Hi, welcome to our next level 3 differentiation video. In this video we turn our attention to parametric differentiation. Two-dimensional parametric equations are a pair of equations, one for the x-coordinate and one for the y-coordinate, using a third variable for the input, which is the dependent variable, and we often use t for time or theta for angle. Now this is pretty new to most of you, but if you have a look at the 4 graphs we've got on the screen, these are all created by parametric equations. We'll show you an example of what parametric equations looks like. Here we have x is equal to t squared and y is equal to 3t. So we have a rule for the x-coordinate and a rule for the y-coordinate, and both of them use a third variable called t. We often use t for time. When t is 1, let's substitute into the x rule. X is t squared, so 1 squared, which is 1, and y is 3t, which is 3 times 1, which is 3. So we get the coordinate 1, 3 when t is equal to 1. For example, when we start a stopwatch, 1 second later, an object is at the coordinate 1, 3. All right, have a look up here at the table. I've plotted some points for different t values, and I've drawn a picture of the graph. So when t is 0, we get 0, 0. The point we picked was 1. When t is 1, we get the point 1, 3. And there's different t values that I've substituted in to get different coordinates and drawn this graph here. All right, let's show you what to do to differentiate these. We have x, which is a function of t, and y, which is a function of t. So to get dy dx, we have to go dy over dt times dt over dx. Now, dy dt is, we differentiate the y rule with respect to t, and dt over dx, we differentiate the x rule with respect to t, and then we have to flip it upside down. And hopefully you can see that the dt's cancel, leaving us dy over dx. dy dx is the formal way of writing y dash. All right, let's get into example 1 and show you how to differentiate these parametric equations. X is t squared and y is 3t. So let's start with dx dt and differentiate that so the 2 comes out the front and drops down to a power of 1. And let's differentiate the y function with respect to t. 3t, a number times a letter, differentiates just to the number 3. Now, quickly up here, we know dx dt is 2t. Let's flip it upside down and put dt over dx. Flip it upside down to get 1 over 2t. And now let's use the formula dy dx is equal to dy dt times dt dx. And let's substitute in dy dt, which is 3, times dt dx, which is the upside down version of dx dt, and we can get our gradient of 3 divided by 2t. Now this set of parametric equations produces this graph, and we could use the formula for the gradient dy dx to find out the gradient at any point on the curve. All right, let's get into example 2. Let's differentiate the parametric equations. X is equal to 2 sine theta and y is 3 cosine theta. Here's what the graph looks like. It's a oblong, I guess some people call it, or an oval, what I prefer to call it. All right, let's differentiate x with respect to theta. Sine differentiates to cosine, so we get 2 cosine theta. And let's differentiate the cosine, which differentiates to negative sine, to get negative 3 sine theta. Let's once again flip dx d theta upside down to get 1 over 2 cosine theta. And let's put these together to get dy dx. So we get dy over d theta, which is negative 3 sine theta, times d theta over dx, which is 1 over 2 cosine theta. And we put these together to get our gradient formula dy dx, which is negative 3 sine theta divided by 2 cosine theta. Well, coming back to what the graph looked like again, it's this oval, and we could use the gradient formula to find the gradient on the curve at any point. Great, thanks for watching.